welcome everyone to the second Orbital Materials Seminar Series. This week we've got Tim joining us. Tim's going to talk about using his use of orb and some other neural network potentials for electrolyte solutions. Tim was previously a research fellow at the University of Queensland in Australia, and he's also been a postdoc at PNNL, the national labs in the Pacific Northwest. He's also just joined Orbital Materials as a researcher as well, which we're very excited about. So I'll hand it over to Tim, and yeah, we're going to have a 45-minute talk today, and then we'll have 15 minutes at the end for questions. So you can post your questions in the chat, and I'll read them out. And yeah, so Tim, please take it away.
Perfect. Thanks so much, Mark. And thanks everyone for joining. It's really exciting to see so many people excited to hear about what I've been working on and where I think we can go from here. And it's really exciting to join Orbital Materials as well. I think they're working on some really great stuff. So thank you, everyone. Great. So I want to tell you a little bit about AI for electrolyte solutions. But before we get into that, I just want to start somewhere a little unusual, which is with Sir Ernest Rutherford, right? One of the greatest New Zealand scientists from all time. I'm from New Zealand. We learned all about him in our high schools. You know, little boy grows up in Timaru, goes off to the UK, and just revolutionizes physics, right? Discovers the structure of the atom, really sets the beginning of modern chemistry. Splits the atom, the first person to transmute the atom, transmute elements from one to the other, right? The first time in human history we've achieved that goal. But unfortunately, he's most famous, perhaps, at least more generally, for this quote, right? Where he says, all science is either physics or stamp collecting. Right? And this is like a quote that physicists, the undergrad physicists, we like to kind of chuckle to each other and feel smug about it ourselves. But there's a lot of problems with this idea, right? One of which is that it's not even clear Ernest Rutherford ever actually said this. It was kind of attributed to him later on. And in fact, he loved the other sciences, right? And he wouldn't have had this kind of disparaging attitude that's implied by this, I don't think. But another problem with it is that it's kind of naive to think that just because all of chemistry and biology and things are physical systems, that they somehow boil down to just being physics, right? It's obviously more complex than that. And the best critique of this idea comes actually from another physicist, Philip Anderson, who's writing in the 1970s, this very famous essay now, and he's talking about this idea of emergence, right? The idea that at larger scales and longer time scales, when you get enough atoms together, you can get these kind of emergent phenomena, you know, life, consciousness, hurricanes, maybe the kind of examples you could think of, things that you see no kind of analog or parallel to kind of in simple physical systems, and which seem kind of qualitatively totally different. And the example he talks about is actually the crystal, right? He says, built from a substrate of atoms in space according to the laws which express the perfect homogeneity of space, the crystal suddenly and unpredictably displays an entirely new and very beautiful symmetry, right? So this has been the central argument against this kind of reductionist picture that this quote from Rutherford implies, right? That just because things are physical doesn't mean that they are going to behave the same way that simple physical systems do. And in particular, we know that in fundamental physics, you know, these homogeneous symmetries are very important, but these obviously can break when you get crystallization forming. And so you can get qualitatively new phenomena which don't obey the same kind of laws we expect fundamental physics to obey. And so this is a fascinating debate. This has always fascinated me for a long time. But there is a discipline of science who just really don't believe this, right? And they keep plowing ahead of it. And this is quantum chemistry, right? And this has been around for a long time. And if you go to some quantum chemistry talks, you know, the central motivating quote you'll often hear is this one who comes from Paul Dirac, right? Where he really doesn't take this argument very seriously. He was writing before this, in fact, before Anderson. And he says, you know, the underlying physical laws necessary for the whole of chemistry are thus completely known. Approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems, right? So his dream is that everything is quantum mechanics. We just need to find a way to solve those equations quickly and fast enough to say useful things about chemistry. And also, I would add biology to here now, right? And so this is what quantum chemists have been trying to do for decades, and they've done a lot of incredible work on this, right? The basic idea is start with the fundamental equations of quantum mechanics, in particular Schrodinger's equation, and find ways of solving it as fast as you can to say interesting and useful things about chemical systems. And although this has been really, really valuable work, given a lot of intuition, it hasn't really transformed chemistry and biology in the way that you might expect, knowing the fundamental laws on which they operate would, okay? And the reason it hasn't transformed it is it's incredibly computationally expensive and demanding to solve Schrodinger's equation, right? When you have many atoms or many electrons, turns out that just brute force trying to solve these equations of quantum mechanics is incredibly challenging. And so this kind of dream, as I call it, has kind of hit this roadblock, right, of computational demands. And so we've always spent many, many decades trying to find other ways to get around this problem, to model chemistry and biology in different ways. But we've never really been able to crack this problem of starting from quantum mechanics. But I think that's about to change, right? I think that is changing, and we're in the process of changing. And I want to argue the fact that I think we're going through a paradigm shift in the sciences more generally, and that soon we're going to see a very different way of approaching a lot of chemistry and biology is going to come about. And this is going to come in particular from the tools coming out of the machine learning field, which are providing us with just incredible accelerations in our ability to simulate physical systems, to solve, the equations of quantum mechanics incredibly quickly, essentially. And that this is incredibly exciting, and that we need many more people aware of this, working on this, and taking these techniques. And the most recent example of this is the orb force field, which was just released by Orbital Materials, that I'm going to talk about later on in the talk. But I'm going to start with some of my own work earlier on, particularly using the NQUIP neural network potential, and just to study electrolyte solutions, okay? And why am I interested in electrolyte solutions? So I've been fascinated with these for over 10 years now, since the very beginning of my PhD. And the reason I'm fascinated with them is because they kind of sit right at this interface between chemistry and physics, and they don't quite fit into either discipline, right? Neither one really kind of wants them. They're kind of too simple for most chemistry, right? Electrolyte solutions, just simple water with some ions in there moving around. Often the ones I'm interested in, sodium chloride, there's not really even chemical reactions going on. It's hard to really argue that this is chemistry. But then on the other hand, it's really too difficult to use, at least for a long time, it's been too difficult to use, quantum mechanics, the fundamental laws of physics, to say much of usefulness about these solutions, simply because you need thousands of atoms to really start to simulate and get the properties of these electrolyte solutions accurately. And this has been too expensive to use kind of quantum mechanics to do, with a few exceptions. But the other reason I care about electrolyte solutions is they're just incredibly important, right? If you could understand electrolyte solutions, there's a vast range of applications that'd be useful for, right? All of biology occurs in an electrolyte solution, huge number of chemical engineering applications, mineral processing, all sorts of carbon technologies, and very important in earth sciences as well, right? The ocean, the equilibrium of the ocean with CO2 is incredibly important as well there. So many, many ways these things are also very practically important. And quantum chemistry has been trying to get at these for a while. And there's various ways you can try and say something useful about these solutions, but it hasn't really had a transformative effect, I would argue, yet. Quantum chemistry really is very useful if you want to look at kind of gas phase chemical reactions. Where there you can do very high levels of theory, solve the equations very accurately, calculate things very precisely. The only issue is that there's just not that much interesting chemistry that really happens purely in the gas phase, right? Almost everything we're interested in is it solids or liquids or some mixture of different phases. And so really it hasn't had the ability to unlock the ability to describe a large range of systems yet. But I think this is going to change. Okay, but before I can get into that, I'm just going to jump in with a little bit of statistical mechanics, right? So this is just some necessary background to understand kind of how we go about solving these problems in physics. So I apologize if you know statistical mechanics. This is going to be kind of a brutal oversimplification, but hopefully it will give hopefully machine learning people a little bit of an idea more of what we're talking about. Okay, so the core of statistical mechanics, StatMech, is the energy, right? This is the critically important function that we want to know. And so the basic idea is, for an electrolyte solution, say, you might have some vectors, which Ri, say, which describes the positions of your ions, okay? And then you also might have some vectors Rw, which describe the positions of all of your water molecules, okay? So these are just vectors. If you had one water and one ion, these would just be 3 numbers each. In our case, we're going to have many, many waters, many ions. And then what we do with those position vectors is we want to plug them into this function called the energy function, which is just a single number, right? For every single coordination state of our atoms, we have a single number, the energy. And this energy is very, very important. It's often called the potential energy surface, is the PES you might see as well, is what this function's called. Okay, and this is really important because if we knew this energy, we could plug it into the Boltzmann distribution essentially and compute probabilities, which is what we really care about in the end, right? We want to know what are the probabilities of finding water molecules and ions in different places, right? What are the probabilities two ions are going to be stuck together versus far apart from each other? And this is determined by the energy plugged into the Boltzmann distribution. Okay, and that's what this exponential is here. Now there's the Z term, which is the normalization term, to make sure it integrates to 1, right? And this is very, very tricky to work out, and this is why it's actually quite difficult to do this, but we've established a lot of techniques to do this over the years. And the classic one is molecular dynamics. And the way it works is you take the gradient of your energy, just how quickly does the energy change as these atoms move, that's the force on the atoms, and then you can use that in a molecular dynamics algorithm to calculate how the positions of these atoms are going to change, right? This is essentially, and then often you'll have some noise in there, which corresponds to a temperature. We use a thermostat. But this is actually very similar to stochastic gradient descent, right? There's deep connections between these two fields. And often we're interested in particular properties of these probability distributions. In particular, one thing we want to know is like conditional probability distributions, right? So that means, say we have an ion at some position, we want to know what's the probability of finding a water molecule near that ion, right? These are called essentially radial distribution functions. And we're going to see a lot of these. We'll see ion-water radial distribution functions. We'll also see ion-ion radial distribution functions, right? So it's the probability of seeing an ion near another ion, for instance. Okay, and these are the core concepts we want to predict. And why do we want to predict those? Because it turns out that those are just very useful for many reasons, right? One thing is you can plug them into thermodynamic theory, things like Kirkwood-Buff theory, and you can compute macroscopic properties that we really care about. Things like how much salt can you dissolve in water, what are ions going to do, and what are electrolyte solutions going to do when you mix them with different things. These are all these practical experimental things we care about could be computed if we knew these probability distributions, right? So that's the core motivating thing we're trying to do. And so how do we get this energy? Well, in principle, we know how to get this energy. You solve Schrodinger's equation, right? That's quantum mechanics. That's the core of quantum mechanics is Schrodinger's equation. This is the time-independent version here. I'm oversimplifying here, but basically almost always what we care about is the ground state energy of this thing, right? The lowest energy value, which solves this equation, right? It's called the ground state energy. If we knew what that was, it would be very, very useful because that's what we could plug into the Boltzmann distribution. Okay, but the problem is, as I said, this is very expensive to solve, right? You need a huge supercomputer to solve it as soon as you have any kind of realistic number of electrons. And so this is kind of where we've been stuck for decades, right? And so instead, what people would use is many different approaches, but basically what mostly we do is try and guess what this energy function is going to look like. And we use all sorts of physically motivated functional forms, 1R, multipole expansions, all this beautiful theory been built up over the decades. But the problem is that they're all just still guesses, right? And the problem mainly they have is even if the functional forms were right, the parameters to plug into those functions are very difficult to know. And often we end up just fitting those parameters to experiment or kind of an ad hoc approach, fitting it to quantum chemistry. But this is called classical or empirical force fields, very, very well-established field. It's done an amazing amount of things, but it does have this fundamental limitation in terms of what are these parameters going to choose. And so we really would like a way of doing this more rigorously and consistently. Okay, then there's one more piece of StatMech I just want to talk about because we'll come back to it later. And this is the idea of coarse graining and free energies, which is another very important idea. And the simplest way to think about this is, so we've got this probability distribution rho, right, of all of our ions and waters. But often we don't care about the waters, right? The waters are just kind of buzzing around there in the background. We really want to know what our ions are doing. And so what we do is marginalize that probability distribution. We just integrate out the positions of the waters, right? So we just do an integral, we integrate over all of those waters, and we'll get the probability of our ions in a given position, right? And then it turns out if you take the log of this, that's actually a free energy. That's all a free energy is. It's just the log of a marginalized probability distribution. It also calls a partition function essentially. And this is the free energy, and this is so useful. These free energies are what we really, really want to know, right? Because if you know free energies, you plug them into an exponential, a Boltzmann, in fact, and you get relative probabilities, right? And so this would be very useful. And there's one other really nice trick about these free energies, which is that they're also called the potential of mean force. Okay, it's the same thing. And they're called the potential of mean force because if you take the average forces on the ions, averaged over all of the possible water configurations, that's actually equal to the gradient of the free energy with respect to the ionic positions, right? This is a very, very useful fact in statistical mechanics. Okay, and so if that's all a bit too mathsy for you, the basic thing you want to know is just that free energies tell you how strongly things are going to stick together in water. And that's very useful, right? What's going to stick to what, right? And this is drug discovery. There's a big problem in drug discovery. You want binding free energies of small molecules to proteins. It just shows up everywhere, right? Okay, so that's the kind of high level takeaway, that we want these free energies, right? Okay, so how are we going to get these? So there's a ton of approaches you can get to try and get these things, right? This is the zoo of different approaches people take to simulate things. Notice most of them can be formulated in terms of molecular dynamics, although it's not often formulated that way. But they all have different scales, right? So ab initio molecular dynamics, ab initio means, from first principles, it means from quantum mechanics, right? Starting from Schrodinger's equation, that's the dream. But you'll notice that's way down there in the left-hand corner in terms of short times, small length scales, right? That means not many atoms, it means small systems, okay? But that's because of the computational demand. But you can actually just brute force it, I call this, right? This is where you just use Schrodinger's equation, calculate the energies and the gradients, and use molecular dynamics that way. Or you can do classical MD, that's what I said, where you kind of guess these functional forms, and that gives you these much larger, longer time scales, although still limited. The problem there is you've got to guess what these parameters are. And then you can do coarse-grained MD as well. Again, you've got the same problem. You've got to guess these parameters, although there we don't really even know what the functional forms should look like. So it turns into a much harder problem. And then you've got continuum mechanics, which is kind of a separate kettle of fish, but coarse-grained MD will kind of get you over a very large spatial scale. And there's things called dissipative particle dynamics, which are basically like coarse-grained MD for very large scales. But we're not going to go there too much. Okay, so this is the kind of hierarchy of approaches you can take. This has always been deeply dissatisfying to me, right? So people have tried to do electrolyte solutions with all of these different methods, and occasionally they'll try and ad hoc kind of use information from one level to inform the higher level one. But it's always been kind of incomplete, and there's been no kind of systematic unified framework for kind of rigorously treating the system or accessing these larger scales, starting from first principles, starting from quantum mechanics, right? It's always been ad hoc. And the dream has always been to find a way around this kind of paradigm of finding different approaches and different modeling techniques and trade-offs between them all. And so how can we go about doing that is what we're going to talk about today. So in the context of electrolyte solutions, if you want to talk about continuum models, the classic theory here is the Debye-Huckel theory, right? A century ago, this last year. The basic idea here is we can actually guess what the free energy between two ions is in water. Just two ions alone in vacuum. This is called the infinite dilution free energy. If you just had two ions at very, very low concentration, took the exponential of this would give you the probability distribution or the radial distribution function. And we actually know from electrostatics that this looks something like this equation here. This Coulomb's law comes from physics, and it's got this dielectric constant in there that's associated with how strongly the water molecules screen these electric charges, right? So this is a very nice idea, and what Debye-Huckel did is they came along and they said, well, if we assume this G for our pairing free energy, we can actually calculate the free energy at higher concentrations and calculate probabilities at higher concentrations and compute practical properties of electrolyte solutions, in particular these things called activity coefficients, which are very, very important in chemistry. And so this is a beautiful theory, really groundbreaking, but it has a number of problems. But the biggest problem is that it doesn't work really at high concentration at all, or moderate concentration even. It's only very, very low concentration. And so this is not really practically useful to any real extent. To do anything useful, you really have to add a bunch of fitted parameters and adjust them to experiment. Okay, and why doesn't it all work? It's because we know that the free energy doesn't actually look like this, right? What it actually looks like is this wiggly energy, right? As these two ions come together, it doesn't have this nice curve. It does at long distance. That's why it works at low concentration. But at close range, as two ions come together, this free energy in water with nothing else around them, just water molecules, they get these wiggles, okay? And what's causing that? That's because as the two ions come together, you have to remove the water from between them, right? The water has some finite size, which is about the width of that free energy barrier there, and that's what those two minima are. Those are the two stable points where the ions like to sit, separated by water and in contact with each other. And this has been the really, really difficult thing to calculate ever since. We've had no way to really calculate what these wiggles are really accurately until now. Okay, and this has been a central challenge. You couldn't really, people have tried to, make Debye-Huckel theory in many ways, but it's very, very hard if you don't know what the short-range oscillations are. Okay, so one thing you can do, as I said, ab initio molecular dynamics, you can brute force this out, right? And I went to PNNL to work with Chris Mundy, Greg Shenter, and Marcel Bayer, and Sean Kathman, and great group there where they do this huge DOE supercomputers, just kind of grind Schrodinger's equation out, solving it every single time step, generating a molecular dynamics trajectory with this. And this works. You can actually get those wiggles out. It works pretty well. It's just incredibly expensive. You know, you need a supercomputer, big chunk of a supercomputer for weeks or months, and you can do like one pair of ions maybe, right? So it's cool, but it's not, you're never going to scale it. You're never going to apply it to many systems. You're never going to really do anything transformative with it alone. We need some other technique to really allow us to kind of scale it, as the computer scientists like to talk about, which is a really important issue. So how does this ab initio molecular dynamics work? Talked about it, but we use a particular approximation mainly called density functional theory, which allows us to kind of do this quickly enough, calculate the gradients of the energies of forces, use Newton's laws to update the positions, and you kind of loop this. And as I said, this has become possible in recent years due to better algorithms software, particularly CP2K is the one I use, VASP is another one. Okay, but we need some way to speed this up, right? And here's where machine learning or AI tools are coming to the rescue, right? And the basic idea is we're going to swap out this expensive solution to Schrodinger's equation, which you do over and over again and throw out the data every single time step, which doesn't really make sense. And we're going to keep all that data, and we're going to train a neural network to just predict what the energies and forces are going to be, and to predict it much, much faster, right? So we're going to swap out that DFT with a neural network potential. Now it's going to be trained on DFT, so we still got to generate our training data, but we're going to use a neural network potential to actually do the simulations. And this means these neural network potentials can be highly accurate with modern GPUs and modern architectures and things like Orb, as we'll see in a minute. These things are starting to get really, really fast. So we can start thinking about doing big systems and really accurate. Big systems, really interesting, looking at different things, which is really exciting. So the neural network potential is just just think of it as a really big function with a huge number of parameters combined with, sophisticated ML algorithms to optimize all of those parameters really carefully and rigorously to big training data sets. Okay, and using these ideas coming out of AI, these are getting much, much more powerful, even though this idea goes back, quite a while to Jörg Baylor and Paranello, who really pioneered it. Now these things are really starting to get more powerful, and it's exciting. Yeah, so the main thing we're excited about, this potentially breaks through this fundamental accuracy efficiency trade-off, right? Allows much larger timescales, much longer timescales, while maintaining much higher accuracy than has been possible previously. And this is why we're so excited about this. Okay, so here's how we apply this to electrolyte solutions. Start with Schrodinger's equation. We use DFT, run short ab initio MD simulations. This is what I did recently in a paper we put out. And then you take those DFT simulations and you train a neural network potential to predict the forces from the coordinates, right? The energies and forces from the coordinates. And then once you've got that neural network potential, you can then run much larger systems with much longer timescales. You can really converge these simulations. You can do it cheaply, which is what's exciting. And then you can do something even cooler, right? So remember I talked about this coarse graining idea. We want to get rid of those waters. Well, what we can do is something very, very simple, right? You take another neural network potential, just the same architecture I used, different hyperparameters, but the same architecture, again, using the QUIP here, and you just calculate you give it the forces on the ions. You can just give it all of the forces on the ions, but because you have this big long trajectory now, it can learn the average forces on those ions. And remember, the average forces on the ions is the potential of mean force. That's the free energy. So it's now learning the free energy. So rather than using a neural network potential to learn the energy, we're now using it to learn the free energy, but it's exactly the same principle, right? It's just a mapping from coordinates to an energy, and you can use the exact same architecture to do it. Okay, then once you've got that, you can run very fast simulations of electrolyte solutions really efficiently. You can look at these probability distributions, these are the ion-ion probability distributions shown here, and then we'll get crystallization out at the end, which is exciting. Okay, here's some technical details. I'm not going to go through it all because I don't really have time. The main thing to know is that the level of theory is fairly sophisticated. We've got good convergence. The main thing is we use a little trick, which is we add those Coulomb interactions I showed you at the begining that worked into Bi-Huckel theory. We actually just keep those in there because we know those are analytically correct, and we just get the neural network to learn what's left over. So not clear how essential that is when you go to the bigger data regime, but we found it helped in the low data regime. So you get highly accurate force predictions with this, which is really exciting. These are that's the DFT level of theory on the X compared with the neural network potential. You can't even see the errors, right? These are well below thermal noise. We're getting highly accurate. And these are not the training data, right? This is from the simulation, extracting samples from that simulation, recomputing DFT. So it's, not out of distribution, but it's from the simulation itself. You can then predict ion oxygen radial distribution functions, right? This is these probabilities of a water molecule being around an ion. You see the bigger ions, they're further away. Those dashed lines are from experiment, from X-ray diffraction. We're nailing those really well. Those are two separate neural network potentials, highly reproducible. So I'm fairly convinced now that if you want to know the structure of water around any ion, it's just a matter of putting in a little bit of effort to get that out. And you'll see we're getting much faster ways of doing this soon as well. So that's exciting to me. This has been waiting a long time to be able to do these things. Another really cool thing now is you then take this model trained on electrolyte solutions and you go and simulate pure water with it, right? So this is the density distribution of a water molecule around another water molecule that first peaks that first solvation layer. XRD's experiment there. MB poles are kind of reference level theory. This is, you can actually do water in a kind of brute force way by hand fitting these potential energy surfaces really, really carefully. And we're just nailing that essentially just for free, right? So that we wasn't even trying to do pure water. We just get that as a kind of bonus, which is kind of a recurring theme of these things, right? Getting extra things for free that you weren't expecting, which is really exciting. Here we have ion-ion interaction radial distribution functions. I showed you these before. Really reproducible, which is nice. And you can then take these, plug them into Kirkwood-Buff theory, as I said, and compute experimental quantities. That's what's shown on the right-hand side there. Those are activity coefficients. This is the fundamental property of electrolyte solutions. It's the thing you really want to be able to predict. And we're getting those nicely in agreement with experiment, particular potassium chloride. They like to stick together much more closely. That's what that big peak is. That's why their activity coefficients are lower. These are actually free energies as well, essentially. So those free energy is much lower because they're more stable. So that's nice. We can get these ion pairing free energies out. Another thing we can do is the coarse grain simulation, right? So these are the coarse grain models, the continuum solvent models where we throw out the water molecules compared with the all atom simulations, and we get perfectly exactly the same distribution functions, right? The only difference is the coarse grain models are a couple of orders of magnitude cheaper, single CPU, converge them really quickly, right? Whereas the all atom ones, you still need a GPU and you still need, a week or so. So this is great too. We can get really fast simulations as well. And this was a really cool result we got. So one caveat here, this is not trained on the ab initio data. We were testing things out. So this is trained on classical force fields that actually do crystallize at these concentrations if you do the simulations carefully. But we were running these simulations, and Junji, the PhD student working, came with this video, right? Or a picture of this. And she said, what's going on here, right? This looks, is it breaking? I don't know what's happening. Looks like some kind of, and you see, this is highly structured, right? That's a crystal forming. That's sodium chloride crystallizing out of solution. It's got the correct crystal structure as well, face-centered cubic. This just blew me away, right? So this is the coarse grain model, right? So there's no waters in here. It should not be able to simulate the crystal. We trained it only on homogeneous kind of liquid phase simulations, and yet it's simulating and thinking, oh, actually, I think this is another phase that I'd be more stable in, and it's going to that phase pretty quickly. And this is actually physically the correct behavior because we were actually running above the solubility. It's just the all-atom MD was too slow to see this, right? So this was really exciting to me. People have seen simulated crystallization with NMPs before, but I'm not sure that people have seen it kind of spontaneously emerge out of a simulation where they didn't have training data on it, right? So the neural network potential has never seen a crystal. It's only seen bulk liquid solutions, electrolyte solutions, and yet it's predicting this phenomenon, right? So this comes back to that point that Anderson was making, right? Crystallization is emergent phenomena. We can't hope to understand it using fundamental physics. Well, here I think maybe not. Maybe just starting from nothing but quantum mechanics, we can start to simulate and see emergent phenomena arise, and we don't have to kind of give up on this idea of simulating everything from first principles, of using physics to understand chemistry and biology, which is what I'm so excited about. Another thing, this is actually what I was most excited about, which is a little bit obscure, but these are infinite dilution pairing free energies, right? I spent my whole PhD trying to get these things out accurately. It's very, very challenging. But so a little bit about details. This is again using the classical so we could carefully check everything. But the black dash line, which you can't actually see, it's under those other lines. This is if you take a full simulation and you do this enhanced sampling and you very carefully compute these ion-ion free energies, interaction free energies at infinite dilution with a classical force field, right? This is what we were trying to get. This is what Debye-Huckel theory was missing, these oscillations, right? And so you can actually get these with the classical force field. We've also now done this for ab initio. I don't have the data yet, but we're going to publish that soon. But so the black dash lines there are the ground truth essentially. And what those other three lines are is we took a coarse grain model trained at 3 different concentrations, right? And then what we did is we took that coarse grain model and we just asked it, hey, what's the free energy? I'm just going to give you 2 ions and just pull them apart in a box. What's that free energy going to be? So a trivial calculation, and you exactly nail this really expensive enhanced sampling, long simulations we had to do to converge it. So you're getting these pairing free energies essentially out for free. Again, this kind of just getting bonus things out that you didn't explicitly weren't trying to get, which is really exciting to me as well. Okay. So this is what I was working on before we worked Orb. The problem with this approach, right, is that you've got to run these ab initio simulations on your systems. It's very expensive. That's still by far the most expensive part, those first 10 picoseconds of training data with ab initio MD. But now we're entering another kind of newer paradigm, and this is this idea of these universal forces. And there's been a few of these popping up recently. Mace Zero was one, the Genome and Madison from Microsoft. There are a couple of examples here, which are all very nice recently. And Orb, obviously, is one of the more recent ones, just come out very recently. And you can see here, really great accuracy. The most exciting thing about it, though, I think, is its speed, right? As you see in this plot, dramatic acceleration in the speed of this thing. And that's really exciting because it starts to open up a lot of possibilities in terms of molecular dynamics simulations, because you can start to access much longer time scales if you can get that speed down. So that's when I saw this paper, I got incredibly excited about it. And I immediately jumped on it and started playing with it. It's non-equivariant, which was surprising to me, because all these other architectures have equivariant. We had a great talk from Marcel. Go back and watch that if you want to learn more about this kind of debate about equivariance versus non-equivariance. It's absolutely fascinating. I'm still kind of learning about these things myself, but it's really exciting to see all of these kind of advances in the architectures coming, and this kind of interesting different approaches coming. Everyone's trying out different things. It's very exciting to see. Honestly, when I saw this, I thought non-equivariant, and also it's a non-conservative force field. I think is another reason for the speed, right? Which I just personally thought, it wouldn't be stable. I would have guessed that that's not going to be able to run nice long simulations. And really another nice trick that it uses is these diffusion pre-training using this kind of denoising objective, which is also very cool, which I think kind of helps with some of these stability issues. But as soon as I jumped on starting to use this, I was expecting kind of it to break, but no, in fact, I saw it started to perform really well. There are a few issues, but we sorted those out. And then, so in the blue line here, this is a water simulation. Again, that blue line is just out of the box what you get if you simulate water with Orb, and you see a nice water simulation, right? Peak positions in the right place, you're getting the right structure, which is really, really cool. It is a little over-structured. You'll see that blue line there, but actually this is exactly what I was expecting because it's trained on PBE DFT level of theory, and we know that PBE slightly overstructures water. So this is totally to be expected. And so that was really, really nice to me. So, and in the training data, there's no water, right? It's all just, well, there's ice probably. It's all crystal structures. It's not like it's been trained on molecular liquid simulations or something. So this is really outer distribution stuff it's doing. Other things have been seen for other force fields, but not with this kind of speed, which is exciting. Okay, and the other very cool thing you can then do is you can do fine tuning, right? So what I then did is took a database of electrolyte solution simulations, so not pure water at all. In fact, quite a complex electrolyte solution one. I haven't even published this yet, but using that same level of theory I used for the previous results, which got this really nice water molecule. So we fine-tuned on that, and then you get perfect agreement with that reference. That reference is MB pol. That's that kind of thing that we know is really quite accurate, and you're getting really nice exact reproduction almost of that now. So that's very cool as well. Really just the issue is the DFT functional level theory, and you can fine-tune, fix it up, and this is really quite cheap to do that. Just a few hours on a GPU, and then you can get a really nice accurate water molecule out with this as well, which is exciting. The other thing you could do, which I also thought wouldn't work, but did work pretty well, is simulating ions as a solution, right? So here, that blue line is out of the box what you get if you just simulate potassium chloride in water with Orb, and it works pretty well, right? You get that right peak position, you're getting the structure qualitatively right, tiny quantitative errors, but you can fix those up again with fine tuning, which we do there. So when you fine tune to that high level of theory, that's what that orange is, you now reproduce that green, which is what we got from those neural network potential simulations I showed you earlier. So this is very, very nice, right? I'm now convinced, and this is because this is going to give us massive savings if you want to go about simulating a lot of electrolyte solutions, right? Because now you don't need the ab initio MD at all. You start with Orb, that's what, I don't know, 1,000 times faster or more probably. And so you can get really, really hopefully now you can start to think about, well, we could just, a whole new world opens up in terms of things you can simulate. In fact, there's just way more things to simulate then. Really now the bottleneck is not computational time. The bottleneck now becomes like researcher time to pay attention to these things. And so that really becomes how much time. That's why I think we need way more people picking up these tools, using these tools. There's just so much to do with them, so many places to look, so many things to simulate. We need probably, 100 times more people working on using these tools, learning how to run MD simulations, because there's so many exciting things to see. So that was really very exciting. A lot of more exciting things that I'm not quite ready to talk about yet, that I'll talk more about later. So a general kind of summary of where I think things are going now, right? So I think soon, or really now, I mean, there's some exceptions, things you won't be able to do yet, but we'll soon be able to simulate any physical system from first principles highly efficiently, which is just incredibly exciting to me. The way you'll do it is something like this kind of pathway where you start with kind of one of these universal force fields that's very fast. You generate initial trajectories with that, and maybe that's good enough. For a lot of things, that will be good enough. A lot of qualitative things, that will be fine. If you really want high accuracy, if you want quantitative predictions of things, you could do some resampling, do fine-tuning with a high level of theory, and then run the simulations again, and get really accurate simulations. If you want to then access larger and longer timescales, I think you can then do coarse graining, right? You run long equilibrium MD simulations, you drop the degrees of freedom you don't care about, just learn those average forces, that gives you those free energies, and that can then allow you to access even larger timescales, even longer timescales, start to see emergent phenomena, which is really exciting. And so I think this is a general kind of technique to apply to many, many physical systems. And the core idea here is that this is a tool for connecting scales, right? So Greg Shenter always used to talk about this, which I never really got at the time, like this problem of how do we connect scales, right? And how do we go from the quantum to the kind of atomistic to the larger scale, right? Rather than using this ad hoc approach where we're building custom models for each different scale. And I think these neural network potentials are the tool to do this, right? Automatically learning energies, learning free energies from the data is going to be the way that we're going to enable this. And that's really exciting. Okay, it's not just me who's saying this. This is another great paper from a guy called Gianni Fabritis over in Spain, who's talking about biomolecular simulations is also going to have a big impact on bio. Machine learning potentials offer a revolutionary unifying framework for molecular simulations across scales, from quantum chemistry to coarse grain models, right? We're on the same page on this. I think this is going to be transformative. Okay, the other way kind of conceptually I like to think about these things is in terms of a computational microscope, right? So I worked in a chemical engineering department at UQ for quite a while, and there's always this frustration when you're trying to design new materials, when you're trying to understand a chemical system or a biological system, that makes it so hard, which is that we just can't see what's going on, right? We don't know what are the atoms actually doing? How are they moving? What structures are they forming? What are they doing one after another? What's actually happening there? And so there's this huge amount of guesswork, and we've developed all of these really sophisticated, beautiful kind of experimental techniques to get at this, XRD, NMR, IR, Raman, all these cool things to kind of try and see this. But in my mind, these are all kind of very indirect, and it's a little bit like we're in a dark room and we're trying to make something in a really dark room, right? And we can't see what's happening, so we're using all these techniques. We're sniffing things, we're licking things, kind of getting indirectly what's happening. But what we really want is just to be able to turn the light switch on, right? Just see exactly what's happening at the molecular scale. In particular, we really want to access this picosecond scale, this angstrom scale, with so many important processes happen, where atoms, bonds form and bonds break, and atoms are moving around, right? There's this one particular scale where if we could just see what happens at that scale, it would be really transformative. And I think this technique is possibly going to provide us with that ability, right? So that's why this is not my idea. I'm not sure who originally came up with it, but this idea of a computational microscope is key, right? The idea that you could use a computer to see what's going on at these scales in a way that you can't access with other kind of techniques, right? And this has always been the dream of molecular simulation. And it has different problems to experimental techniques, right? The problem is your level of theory accurate enough? Can you trust what you're seeing, right? It's very easy to see what's going on. The question is, can you trust what you're seeing? So it's not a silver bullet, but it is a powerful new technique in the arsenal of our ability to understand material systems, to design materials and chemical systems and biological systems. And that's what I'm really excited about. Okay. And so one example of this is in these simulations. One cool thing we saw was just lithium pairing, right? Two lithium ions coming really close to each other in solution. You don't see this at all in classical simulation. It totally goes against conventional wisdom. These things are meant to be strongly hydrated ions, strong hydration layers around them. But you can kind of get rid of those hydration layers, and they'll just kind of come together really nicely. I don't really know if this has any implications, but it's just a nice kind of surprising thing that drops out when you can just actually look at these simulations and see what's happening in them, which is very cool. I've seen a number of really remarkable things like this now. As I said, I haven't published these yet. I'm a little bit nervous that they're kind of hallucinations or the neural net potential is going off the rails. I'm just trying to do some more work to validate them. But there's going to be more stuff coming out really soon. We'll be using these techniques, using Orb as well to really show some really surprising things that we would not expect. When you run these simulations, you can see what's happening at these scales, which is really exciting. Okay, one other analogy I'd like to make just to kind of build intuition about this is like the way we used to design bridges, right? So back in the day, like 100 years ago, when people were building the Brooklyn Bridge and things like this, we didn't have computational models of bridges, right? So everything was kind of a lot of trial and error, a lot of intuition and guesswork, and we ended up like massively over-designing these bridges, right? So it turns out that the Brooklyn Bridge is going to stand for an incredibly long time just because we didn't know like what the actual limits were, so people ended up just using a huge amount of extra brick and wires and things, far more than we needed. And I think this is the kind of state that we're in currently with designing materials design and biological systems a lot of the time, relying on trial and error, guesswork, a lot of kind of guesswork and intuition, and we end up over designing things a lot of the time or finding solutions that aren't optimal. But once we built computational tools that could really accurately model all of the forces on the beams of a bridge and the wires and things, you can then start to do really incredible and amazing things. You build bridges that are far taller than you would have thought possible, that are really minimalist and are approaching the limits of what you can do with bridges because you can computationally model these things. And so that's where I want to take chemical engineering, the ability to design materials and biological systems. We're going to find what the limits of these things are, which is going to be very cool. And I think it's coming. Okay, so to sum up, I think neural network potentials are a powerful general tool for connecting scales in physical simulation. I think it's now possible to simulate a vast range of systems efficiently, starting from nothing but fundamental physical law. And this could provide unprecedented level of new information. And there's still problems, there's still a lot of challenges to be overcome. There's still many things you can't do with these techniques yet. But I think there's a ton of things you can do. And when these new techniques coming out, the thing to think is, what is it possible to do with these now, which hasn't been possible, because there's just so many things to be done with them. And really, I think every chemical manufacturer, every drug company, materials scientist, and chemist should be beginning to get their head around these tools, what they can do now, and starting to run these simulations of these systems now, because I think already interesting insights would drop out if you could run these simulations of many systems that many people care about. And the important point to make is that there's no data wall here, right? This is not like LLM scaling where you kind of have, only a finite amount of text to train on. Here we can generate our own data in a kind of automated, efficient, in the loop kind of way, generating new quantum chemistry data. These tools are still only just beginning. There's really a huge amount of fairly low hanging fruit still to come, I think, in terms of what you can do with them. And so, yeah, it's a very cool time. And I will finish there. Thanks very much.
Great. Thanks, Tim. Okay, so if people have questions, you can just write your question in the chat. Or actually, maybe let's see if I can individually unmute people. Okay, let's just go with questions in the chat for now, I think. Also, Alex.
Yeah, paper preprint. Yes, the electrolyte solution stuff that I did with the Quip. Yes, that's a preprint. I can put it in the chat. I haven't published the Orb stuff yet. There's still a lot to do there. But yeah, definitely, I think we'll put a preprint out at some point on electrolyte solutions. Yeah.
Cool. Andrew is asking, are these results I presume we're talking about the orb models here. Are these results from the V2 models?
Oh, yeah.
Yeah, almost certainly yes. We had some. There were some serious issues with the V1 model, so I basically recommend that people do not use them at all, particularly the simulation.
The potassium, yeah, I would use the V2. The potassium was definitely V2. I think the water one might have been V1 actually, because I did that right at the start, but it seemed to be fine. But yeah,
cool.
Yeah,
cool. Kareem is asking, I managed to use the orb models well using ASC. What about CV2K and lamps? I can probably answer that question.
Yeah,
so,
that was a big one. Yeah. I also have that question.
Actually, someone contributed an open source wrapper for lamps, I believe. I can I'll add it to our GitHub repo actually, as a note pointing people to it. It's basically a wrapper for running orb models inside a lamps MD simulation, because I know that there is a bunch of kind of MD configuration that you can do in lamps that you can't necessarily do in ASE directly. So yeah, we haven't actually used that yet ourselves, but yeah, that's
Nice.
where I would start with that. Okay, Olaf is asking, how would you move from electrolyte solutions to pure ionic liquids and to water and salt electrolytes?
Yeah, great question. So we did a molten salt that worked really well. Just heating the temperature up, sodium chloride. It's actually easier because the hard thing about electrolytes is you've got this low concentration, right? So most of your box is water, and so you actually don't have very much training data at all on the ion-ion interactions. And so there's an interesting optimization question about, do you want to go to higher concentrations to get more training data and things? But yeah, so that was the main problem I had getting the stuff working in the early days, was just getting training data of the low concentration stuff. I think going to molten salt ionic liquids should be easier. Water and salt electrolytes similarly, yeah, I think they should be easier. Now there is there is the challenge of electrostatics, or the long range electrostatics, and so this is still an open question as to, so orb doesn't use any explicit electrostatics or explicit charges. So it'd be an interesting question. It'd be actually really interesting to look into how do they do for ionic liquids. I think they would get the local structure really well. I know ionic liquids can form kind of maybe longer range. They form some kind of, there's a thing called the Kirkwood line. You get these interesting long range structures forming at high concentrations in electrolytes sometime. So it'd be very cool to see if they can reproduce those things without explicit electrostatics. But the other option as well is you can add in explicit electrostatics and then kind of fine tune the model perhaps on the non-electrostatics piece, and then keep that in there. But yeah, there's a ton of interesting questions to look at with ionic liquids, water and salts. It'd be very cool. I think it should do an okay job.
Nice.
Yeah.
Alex is asking, have you tried running the CG models for sodium chloride below the solubility limit?
Great question. Yeah, we should do that. Have we? I don't think we have. It took a long time to see that coarse grain one. So I don't actually know why. Ginger was just running it for ages. I would have stopped, but she was running that one for a long time before it crystallized. Not about a long time. It's very cheap. Yeah, but it was actually like very well fully converged, and she just kept running. So I suspect what would happen is you go to lower concentrations, but you have to run it longer and longer and longer, obviously. What we want to do is actually use it to calculate solubilities, which it seems like it should be possible to me. It should be it's like a very simple way to compute solubilities, right? So you could simulate that electrolyte and look how much of the ions are in the bulk versus the crystal. Look at the concentration of ions. We have some indications that this works okay qualitatively, which is nice. I think we need to add fine-tuning data for the crystal to get those quantitatively correct. So I don't think it's going to get the solubilities quantitatively correct. It looks like it's the right order of magnitude, though, which is nice. So I suspect as you go to lower and lower concentrations, it would just get harder to see that nucleation events. It's hard to prove that it would never nucleate because you have to run it forever, but it would definitely take longer and longer. But yeah, that's an interesting question.
Nice. Martin's asking, is the orb model that was trained on R2 scan showcased in the presentation publicly available? To my knowledge, the model was only trained on Alexandria PB and or Materials Project PB.
Yeah, so yeah, I fine-tuned that model myself on just electrolyte or just on electrolyte solution data. So it's not a universal model now, right? Because as soon as you fine-tune it on that one piece of data, it's probably going to do weird things to the out of distribution stuff. So there's not a universal model at R2 Scan now at all. That the one I fine-tuned is probably going to work for that, only going to work for that system, I assume. As far as I know, right, Mark, there's only a PBE one. There's different dispersion corrections, right?
Yeah, I would say watch this space, because models that can handle multiple levels of theory are in our kind of pipeline for the.
Yeah, that'd be really cool. Yeah.
So this is something that we have actively kind of working on.
Yeah, but I'm happy to share the electrolyte solution data. I put all the code up. Yeah, but I need to share the training data sets as well. I just find someone to put those up.
Well, Ashwin is asking roughly how much computational data do you need to train these models? I'm assuming, Ashwin, you're talking about the fine tuning here.
Yeah, well, maybe we could answer both. I mean, you could talk about how much orb needed.
Right, yeah. So orb is pre-trained on a large set of kind of. This is all in the technical report. So just pre-trained on a very large set of crystal structures. Some molecular systems as well. And then in terms of the actual data that has, DFT trajectory data, is Alexandria combined with the Materials Project data. So I'm not actually sure how many systems that is off the top of my head. That's the kind of training data. Ben is,
yeah, 30 million,
30 million.
Yeah. So Orb has big.
Probably not quite that much, but yeah.
Big data sets, yeah. In terms of the fine-tuned ones, I actually use the same data set I use to train the equip ones. So in some sense, it's not that surprising that it works. I guess it's a good architecture, so it's going to do a good job. So how much was that? That was around 10 picoseconds of ab initio MD, plus I took a 1 nanosecond neural network potential MD and resampled with it just to get some additional, more diverse training data set. So it was around 600 frames of a electrolyte solution simulation with that high level theory. So it's basically you can get it on on a day with 100 CPUs.
Nice.
Was for a single electrolyte is the kind of costs, I think. So yeah.
Martin is just asking for clarification that you took an existing orb model that was trained on PBE and then
exactly
on RT scan data.
Yeah, on scan data.
In general, this works fine. We tested this internally, and Orb has no problem fine tuning to different levels of theory. And you also see a nice boost, regardless of in terms of if compared to starting from scratch. If you were to start from scratch with the same model, you generally see more accurate model faster when you start from Orb, regardless of the level of theory. So
I did not start. It would be interesting to try starting from scratch with the Orb architecture. It would probably do fine as well. The thing I really like though about it is I didn't mention this, I probably should have, but some of my equip simulations, I see some stability issues when I go like over a nanosecond, like maybe one of the ion pairs will hop together or do something unphysical. And this is just kind of annoying, but I never really see that kind of things with Orb. And I think it's because it has this huge database of things. It knows that that's a totally unphysical thing that will happen. Whereas if you just give it these really short ab initio trajectories and that's all it has to go on, as soon as it gets out of distribution, it can break and do weird unphysical things. So I think that really nice, that stability is a big relief, because it's a real pain when you've got a nanosecond simulation and somewhere in there, like one atom has done one annoying unphysical thing, and then you got to either throw the trajectory out or try and salvage it somehow. So it's a real lifesaver to have just really stable simulations. You don't seem to have to worry about that kind of thing, which is really nice.
Cool. Rajni is asking if mixing data from different DFT codes affects models' performance during fine tuning. I would Yeah, that's a good question. So I would suggest try to not do this. It's very fiddly. We've tried this before, and it's difficult. You have to be very, very careful about a lot of different measurement scales and things like that. So
yeah, especially because VASP and CP2K are like quite different.
Yes, right.
It's not just like a different code doing the same thing. It's a different like mathematical, like different theory, right? One's this hybrid basis set approach. The other's pure plane waves, and the pseudo potentials are different. I mean, it's so different. Yeah, you want to be very careful about that. And another point is like by far the biggest problem I have is noise in my training data, right? Like at least 90% of the time, it's like, oh, I'm like, what's wrong with this? What's wrong with my neural network potential? It's like, no. You use the wrong cutoff in your DFT, or your pseudo potential is bad, or it's not actually the neural network potential. You're just feeding it bad data. I mean, this is the universal lesson, right? But data is king. So yeah, really paying attention to getting really nice, clean, consistent data, I think is a key lesson that I've tried to learn.
Yeah. Cool. For the Orb D3 models, do you think you can also introduce a model based on non-local functionals? Yes. Yeah. That should be possible. Again, that's like something that we're working on, kind of for V3. Yeah, the models have receptive fields that should be large enough to capture these types of non-local interactions as well. So, although
yeah, as long as are they in VASP? Probably, I guess they are.
Actually, that's true. Yeah, it does probably require that they're. I'm not familiar enough with VASP to know that, but
they probably are. Yeah.
Yeah. Cool. Cool. I think some of these questions are now more about orb models. Kareem, what do you think should be the correct approach if I'm dealing with systems needing a DFT plus U correction? Tim?
Yeah, that's a good one. So you're asking, I mean, you could generate DFT plus U data, right? And just train your potential on that. I think that should work. If you're asking, yeah, so I assume you could use Orb, get your initial structures, and then generate some, resample from that, redo the calculations with DFT plus U, and then fine-tune a model, fine-tune it on that. I think that would work, right?
Yeah. Okay, Martin's asking, isn't the reason for not mixing VASP and CV2K the same reason for not mixing RT scan with PB? Okay, I think that a bit of a clarification here. When I was saying this works well, I was talking about fine-tuning a model trained on one level of theory, on consistent data from another single level of theory. What the thing that doesn't work here is mixing your training data that is either at two different levels of theory or from two different DFT code sources, right? And then expecting that model to work better, or
Yes. So I took Orb, which is trained on VASP data, I guess, and I fine-tuned it on CP2K data, and that worked fine. So you can do that, right? But you can't just do CP2 and VASP data at the same time in the same
combined. Yeah, exactly. Yeah. Great. Okay.
There's some good info about DFT plus U. Yeah. I'm not a DFT plus U expert, sorry, but yeah, that looks interesting.
Cool. Well, yeah, Tim, great talk. Thanks for coming to talk to us today, and thanks everyone for joining.